Hello, this is Edgin Montiel, and this video is for Dr. Christopher Foley's MAE 1503 Introduction to Engineering Design. And this video is picking up where the last one left off, where we were doing the tutorial in SolidWorks for the stress analysis lab, where we're doing all the different parts. We already completed the hook. And when we look at Dr. Foley's assignment here in Canvas, so we should have already been able to answer question 1, so you should understand what a factor of safety is. And then number 2 is we're going to want the analysis report from the hook that we created in part 1 of this video. So again, that was by clicking on this generate report button. There were some other things that we could do in here, but that was all that was required for this part. So now I'm just going to close out of it. It's asking me if I want to save my data, and I already have the report, which is required for the assignment. So I'm going to say no, because I don't want anything beyond that. Now I'm done with this part, so I can come up here to File and go to Close, or I can hit Control W on my keyboard. And again, this part is loaded in SolidWorks, so depending on how you opened it, you don't want to override the one that you opened in SolidWorks. So you hopefully maybe saved it somewhere separate, so as you were working on this, it didn't create a bunch of things inside of the root directory of SolidWorks. But if not, just don't save this part if you didn't know what that means. Like, don't change the root directory of the hook in SolidWorks. So I'm going to hit don't save, even though I downloaded that part, because I can always just open it again if I need it, because I could download it from Canvas again and open it. So now we're going to move on to the second part, which is going to be this control arm, I think is what they call it. So I had already downloaded the part for the last video. Let's see if I can find it. It may be easier just to go get it again. Where did I put that window? So close and download. We're going to open it here. And here's all the parts. This time I want the arm. So I open that up in SolidWorks, and it's the same part. Yay! Now here again, you can open up from SolidWorks. Just if you open it up this way, make sure you save it somewhere separately so you don't actually override the one in SolidWorks so other people can use it, or you could do this again. What's cool about this one is that it's going to show us how to make our own material properties, or how to enter our own material into SolidWorks. This is very useful because SolidWorks comes with a lot of materials, but especially in the world of polymers, we're still creating new ones. So those new materials are going to have their associated material properties, and so they don't exist in the computer yet. So as we make new things, we need to be able to put them in the computer, especially as we analyze them, and probably as the science improves, we'll be able to fine-tune these numbers even further to make them more accurate in our modeling in computers. So we're going to, part of that, I'm going to end up going back to this window because this is the best way to look at it, in my opinion. So in the feature design tree, right-click the part name at the top of the tree and select document properties. So here is the design tree again. This is the part. You can tell because it's the little Legos next to it that's identifying it as a part. So I can right-click on my part here, and it wants me to go to document properties. Under document properties, click on units. Under units, click MKS. So and then hit OK. So that's the first step it wants me to do. Then we're going to do the same thing. So again, in SolidWorks, there's like 900 ways to do the same thing. So I can click on this one, and it shows that there's actually an edit material button up here. But I can also come right here to the material and right-click on it and get to edit material this way. This is the way I like to do it. So it wants me to create a new library, and I've already done a bunch of these. So I'll just make another one. So you could right-click anywhere on here. I don't want to accidentally associate it. So I'm going to right-click down here so I'm not accidentally selecting something. And I can click on New Library. And now this is where I want to save my library. And you can see I've made this video a couple times, so I'm just going to call New Today. So hit save, and now I have a new little folder here called New Today. Now I can click on that one because I want to make sure I'm working with that, and I can right-click on that and put New Category, and under New Category, the instructions tell me to name this one Still Like Materials. And then I can just hit enter on my keyboard to have it select that name into place. And now it wants me to go into the SolidWorks materials under Still and get Alloy Still and copy it. So under the SolidWorks materials, under Still, under Alloy Still, I select it and I right click on it and I can copy. So then I can collapse all this again and go back to my new one. And when I right click on that one, I can hit paste, maybe. Paste. And now it moved that alloy still here. And it wants me to rename it to still 1. For example, still 1. Still 1. Sure. Still 1 today, in case I already have it. So there we go. And then here's where it wants me to enter the new stuff, because now I can actually alter these material properties. And there's a lot of material properties here. But usually for calculations, you'll learn later on in your engineering disciplines that as long as we know 2 of the properties, we can pretty much figure out the rest of them, because they're all kind of related in one way or another one. But they have to be specific. They have to be independent properties. One of the most important ones is Poisson's ratio. I love the name Poisson because it was like a French guy that came up with it. But this one's a very important material property. Each material has its own unique Poisson's ratio. So I'm going to actually go back to that other window, though, because I like to look at this way, just because I like to make sure that I am in Newton meters squared, which is pascals, so that all of this stuff will line up, and the kilogram meters cubed there for the mass density. So these are all correct. And I want to make sure that I can alter these to what they want me to be. So this first one, the elastic modulus, it wants me to change this value to 1.2 E11. So what that means is 1.2 times 10 to the 11th power is what this value is in Newton meters squared. So you could just type in that easy. Poisson's ratio is 0.028. So to actually edit these, I have to click on the numbers. Like if you click over here to the right, it like highlights it, but I don't think it actually lets you edit it. So you want to make sure to click on the numbers there, and we're changing this to 0.3. Then under yield strength, we're going to come and change this one as well. This one says 5E8. So I could just type it in like that. When I hit enter on my keyboard, it actually changes it to that big number. And then mass density, which is this one, we're just changing to 7,500. So now all of that is updated. I can hit save, and I can hit apply. I selected this one. Don't yell at me. Apply. So I selected it over here. It was mad the way I did it, apparently. So I applied this one, hit apply, and now I can hit close. And now we can see that it changed color and stuff in the background. And I can actually see that my material assigned to, again, here's my part. Everything listed underneath it is the design tree for this part. This is the material for this part, and I can at a glance see that I assigned it to still 1 today, which is the thing that I just made. So I got the material properties all done. Save, apply, close. Still 1 is assigned to the part. And now we want to launch the SimulationXpress wizard. So again, remember it's on evaluate, and you might have to get to it one of the 3 ways that you can get to it. Also, if it's been a while since the last one, so just make sure that under tools and add-ins, you have that little box unchecked, so in case your SimulationXpress didn't launch, and I just forced it to close. We'll load it again. So we want to do options right off the bat and switch it to SI units is what it wants. And then I got to make sure I am saving this in a spot. I think, oh look, stress lab. So we'll just save it in here. So select that folder, and then make sure that select it. So make sure that this little box is checked, and then hit OK and next. And now we have to add a fixture. This one's easy because it's this big part of the control arm. So I just select that and hit check mark. Remember, a fixture is where it's going to be rigid. It's not going to move at that point. So then we're going to move on to loads and hit next. And we're going to add a force. And this time we want the force applied to this little portion of it right there is where it's trying to show us. And then we want to select a direction, and in this little blue field where it's automatically populated for us, we want to click on this top, I believe is what it wants. Yep, top plane of players for the direction box, and then type 4,000 under SI units. 4,000 newtons is what we want. So then I hit check mark under force, blah, 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 going to the materials. But look, we already signed the material. You can see that it's still 1 today. So we already did some of the work. So I could just hit next. And then we hit run simulation. And then it runs the simulation and go, makes the action. I'm going to hit stop animation. Yes, continue. And now it's talking more about the factor of safety here. So with the 4,000 newtons I loaded it on, I could produce a factor of safety of 6.52, which is just a little off of where they got, but it's close enough because each calculation is a little different. My mesh density is probably turned up a little higher than theirs right now. So just like before, we can look at the von Mises stress and the displacement of this part as it's getting loaded, because it's applying a force just like that. It would start to bend, as you can see. You can stop that animation and look at this one as well. You can see that this part is actually doing very well under the force that we subjected it to, and it's going to fail kind of simultaneously at both of these ribs that are created on it as we start to load it up. So I can stop the animation, but then I can click on this one. So what this one is showing is that right now I have 4,000 newtons times 6.52006 is the force that would need to be applied to this before it would start to fail. So we can actually calculate that for sure. So 4,000 times 6.52006 equals. So this would need 26,000 newtons before it would fail. So if we want to know where it's going to start to fail at 6.52006, we could type that value in. But it's going to be like at 1 molecule is where that's failing. So we have to go at least a little higher than that. So we're going to go 6.6, and now we can actually see the little red dot start to appear on our picture, because that's where this part is going to start to fail, is on that one little spot right there. That's kind of a weird spot. It's not so sure where you would expect it, in my opinion. But then as we exceed the maximum load, so if we actually put the 4,000 pounds times 7 on this thing, it's going to start failing here, and that's a lot more dramatic. Just from the 6.6, you just saw it 6.6, it was one tiny little dot. Oops. Right there, and now, so we can just watch it grow as we increase the overloading of it, and seeing just, it starts to fail super fast. 6.7, 6.8, 6.9, we can go crazy and say, what if we put 100 times, and it's just going to like rip it apart. So that it would fail everywhere, because that's just way too much weight, because it can only hold a maximum of this based on the material properties that we assign to it. So that's what this is trying to show you, is where it will actually fail. The instructions tell you to use 8, so you can see right here, it looks just like their picture more or less. So you can just analyze the part a little more, understanding more about it to where it's going to fail. And as you can see, this middle part isn't failing at all. So that's the point that SOLIDWORKS is trying to make here, is that really the forces are being distributed along the frame of this thing, so we can actually go and remove some material. So over here, we do have our design tree, because we're not actually doing anything, and there is this extrude cut 2 that it's talking about, and we can edit that live on the fly, and SOLIDWORKS tells us to do through all and check mark. So now I'm looking at the SimulationXpress study that I already produced. So this is why that center of my part is still there. But I can actually come down here. I have these little tabs on SOLIDWORKS, and I can go back to my model. And right here I can see that it has the middle cut out. So now I want to go back to my SimulationXpress. So I can hit return, rerun the study, because now that the part's different, and now it's going to be mean to me. Let's just go back to this tab, and we're going to go start over. But ultimately, if SOLIDWORKS isn't being nice, you can use it. Sometimes updates it in SimulationXpress to where you can rerun the study super easy with the piece that's now removed. It was just mean to me, so ultimately, you want to remove the piece on your part under model down here. And then when you're back in SimulationXpress, sometimes you just have to hit start over. And as you get good at this, you'll be able to go a little faster to replicate all of the steps. Oh no, we already did that. Replicate all of the steps that we want in this again, because it's only a couple clicks, right? Not so bad. I'm going to do this again. Maybe it's an error I made. I'm not 100% sure. So that next. Oh, we have to choose our material again. We want to find the one Edgin made today. What was it called? New today. Rerun the simulation. Does the same kind of movement, so just like we expected. Except now our factor of safety is significantly less. So even though that rib in there wasn't failing, it actually was holding a lot of the part together. So we can keep going. See, it's supposed to give you like this little thing where you can rerun it again. I don't know, maybe I missed something. So follow these instructions for that part. It might be a little easier than having to start over. But the new minimum factor of safety is 1.4 is what they show. I came up with 1.5. Let's see if I can get closer to their results by altering it. Was it under run? Change settings. Change mesh density. Yeah, I know, it'll erase it. Oh no, that was already fine. Or right in the middle. Let's make it more complex and see what happens. It'll probably make it higher. Loading, loading. Yeah, whatever works. Oh, so it's actually a little lower now. So I went too far. So it just depends on your settings, is what it's calculating it. So done viewing results. And now this time for Dr. Foley's assignment, let's go look at that again. Where did it go? Here, this one. So for this one, he just wants the E drawing file for the control arm. So this is the generate E drawings file. And you want to make sure you understand where it is saving it to. So make sure all your files stay together so they're easy to turn in. And this saves it as a particular, the ending is there. But ultimately, it's this special little file that can be opened because you can actually hold down your middle mouse button and manipulate this and look at the report on it. And it's different values here. There's different things that you could do in here to look at all the different values. So it's just kind of a cool report. You can zoom in and out, all that stuff. That communicates a good amount of the report without actually having to have SolidWorks or a super beefy computer, because like SolidWorks is very intense. This little program that it loads right here that can let you actually interact with this part doesn't require a lot of memory or computer intensive stuff. So if you're doing like a presentation or something and actually want to do a real 3D view, or you're trying to show your boss in real time what this part is performance and where it's going to fail, this is something that you can generate and actually communicate this relatively easy, which is what we want you to do. So make sure you save this one, and that is what you need to turn in for the Dr. Foley assignment. Now we're going to keep going. So generate it, hit save, congratulations, you're done. Go on to the next one, which is the anchor plate. So now we're going to open up that part, which, where is that? So here they are, the plate, I assume. No. So the anchor plate, the instructions get a little more vague. So, because it's the idea is you need to get more proficient at this stuff, but same as always, you just need to be able to replicate all of the same stuff. So it doesn't really matter the order that you do this in. I'm going to do it all through SimulationXpress. So I'm just going to open it up. And let's see, it's wanting me to do 350 pounds. So I know that's English units. So I hit OK, and it was saving it in a good spot. You also wanted to make sure that this box was still checked and that you're saving it in a correct spot. And I hit next, and I'm going to hit add a fixture. And it wants me to fix it at all 4 holes. So 1, 2, I'll get out of the way, design tree. 3, 4, 1, 2, 3, 4. I can hit check mark. So we're done there. Hit next, add a force. So we want to add a force on here, because this is supposed to be like attached to the wall, and you put a bar on here. So the force is actually going to be pushing down on this plane, and it's not going to be normal to it. So we have to do the select direction thing again and find a plane that makes sense, which is this one. And now it's going the wrong direction, so I want to flip that as well, reverse direction, because the force should be going towards, going down. And it wants me to put 350 pounds on it. So 350 pounds of force. So that all looks right now, so I hit check mark. And now I'm putting a force there while having it like fixed to the wall. What that's replicating, very similar to the bracket assignment that we're doing. And then hit next, and this is where I chose to assign the material. You could assign it the other way that we did. But this one is a plastic, and it's this nylon 610, so I hit apply and close. And now it's made out of plastic, and I can hit next. And I'm just going to hit run simulation. I think that was at And now it's talking about factor of safety. All right, so for this part of Dr. Foley's assignment, I think he wants determine the maximum force the anchor plate can support while maintaining a factor of safety of 3. So what you got to do for this part is you have to understand that you're applying 350 pounds of force and that it's going to produce a factor of safety of this. So if you multiply those two together, that's the total force that this can withstand, and then you got to divide it by 3, which is your new factor of safety that you want, and that would be the answer to this one. So this is as far as we have to go in Dr. Foley's assignment, is just to be able to calculate the actual maximum force that this can withstand while maintaining a factor of safety of 3. So that one was pretty straightforward. Now we're going to go on to the spider. I don't think I missed. The only thing maybe that's worth noting is that this is all theoretical stuff, so it's assuming that the material is perfect. There's never a perfect material, with the exception of maybe like a turbine blade, since we actually nucleate those from a single crystal when we're making some of the gas turbine blades nowadays. But most materials don't have perfect crystal lattice structures or crystal, not even crystal, just perfect structures holding them together, because plastics are polymers and those could be like chains. So they're like not uniform in any means. So this is assuming that they're uniform throughout, which is a perfect calculation. So we can always assume that the real maximum force that this is going to be able to withstand is going to be something less than SolidWorks predicts, which is why factor of safety exists to begin with, is because we never design with a factor of safety of 1, because if we model something and say it's going to hold 100 pounds, and it's supposed to hold 100 pounds, that when we make it and we go and put it into use and we put 100 pounds on it, it's probably going to break, because no material is perfect. So we actually have to design it for like 110 pounds, and then we're going to put 100 pounds on it knowing it won't break, because we have that little bit of wiggle room. So that's that one. On to the spider. I'm just going to keep going here. We're going to fly through these a little bit. So this one on Dr. Foley's assignment is wanting us to evaluate it using all the holes fixed, 2 holes fixed, and only 1 hole fixed. So we got to figure out the based on a factor of safety of 2, determine the maximum force the spider can support when. All right. So just like before, this one we want to assign an alloy steel. So I'm going to do it the other way on this one. So you can actually go to material right here and hit edit material. And I'm just going to pick the alloy steel that is in SolidWorks, hit apply and close. And now it is made out of alloy steel and it's so pretty. So then we're going to start with the 3 holes. So I want to go to my SimulationXpress. It's wanting me to load it up with 500 pounds, so I know I'm in English units. I'm making sure I understand where it's saving so I can get to it, and I want to make sure that box is checked. And then I hit next, and I'm going to add a fixture, and I'm going to start with fixing all the little holes here. 1, 2, and 3. So 1, 2, 3. Hit check mark. And then I'm going to add a load. I hit next and add a force, and we're adding an axial force. So this would be a normal force because, as you see, the arrows are pushing perpendicular outwards. So if you could think of this as a pressure vessel, like a cylinder, and we were filling it full of air, that's how that, and it's building pressure on the inside, and the force is coming from like the middle or from the inside. That's what this is replicating right now, which is wrong. So we want to select the direction, like always. SolidWorks usually doesn't get it right, and we want to pick an appropriate plane. I think it was this one, which now that makes sense, because if I zoom in, you can see that it's an axial force. I really don't think it matters on the direction, but we want to make sure that it's 500 pounds here. So you can actually have this going towards us or into the screen here, I think, on the direction. We may try both in the video just to see. Oh, 500. And then, so we're done adding the force, hit check mark. So one of the biggest mistakes students make, I probably should have mentioned this earlier, but over here is they'll add, so I have all 3 defined in one fixture, and I'm going to edit this fixture, but sometimes students will replicate these, so they fix the same point like 3 times, and it totally messes up your calculation. Or same thing, if you add a force there, and then you go and add another force there, and another force there, it's really like tripling it. So just make sure you understand what's going on in your SimulationXpress study design tree here, that you only have the 1 fixed spot and the 1 force. You could potentially do all 3 independently as fixtures, so you can have fixed 1, 2, and 3, and then you could maybe even easierly or more simply be able to delete them from the design tree. But this is the way I chose to do it. Maybe I'll show the other one as well, so you guys can understand what I'm saying. But that was adding the force, so I hit next. It's already assigned the material property at the beginning, so I hit next, and now I can hit run simulation. And so Dr. Foley wants to know what's the maximum load this can support with a factor safety of 2. So I just take this 500 pounds of force that I entered, and I'm going to multiply it times the factor of safety that I came up with in SolidWorks, and then I'm going to divide that value by 2, and that would be the answer for all 3 being fixed. Now I can come over here to my fixed and right-click on it and hit Edit Definition, and I'm just going to remove one of them. It shouldn't matter because it's all symmetrical there. And so now that I removed one, it automatically knows I need to rerun the study, so I'm going to rerun the study. And now I have my 500 pounds times my new factor of safety, and then I could divide that by 2, which is the maximum load this would support with only 2 of them fixated. And then I can come in here and edit this again, edit definition, and remove the last one, delete, hit check mark, and now it's only fixated in one spot, and I can rerun the study again. And now that it's running, and you can see each time it's going a little differently, just like I expected it, because this whole thing is going to bend now, because these are no longer fixed. It's only fixed over here. So now I can take my 500 pounds times this factor of safety and divide that by 2, which is the result for the last answer for Dr. Foley. So again, what I was saying here in the beginning is that the fixtures, I could have independently created them. So add a fixture, made this one, hit check mark, hit add a fixture, made this one, hit check mark. And now I have the 3 fixtures independently. So this way would be correct because each one is only 1. But a mistake students made is they'll make each one of these all 3. So really you're like pinning all 3 each time. So it's like 3 times as held, which messes up calculations. It just doesn't make sense. Same thing with the force. You only need to do it once. Make sure you don't accidentally replicate it. So now I have each one listed there, and I still have everything else the same. So this would all just still work the exact same way. I think that's pretty close to what I got before. So then I can come over here and just delete one at a time now. And then rerun the study. It was like 6 something the first time. It was 1 something the next time. And then I can delete another one. And I think it was less than 1 this last time. And rerun the study. So as always in SolidWorks, there's like a million ways to do the same thing. And I think that's pretty close to what it was. So the other thing I said we could look at is we're going to edit this definition. And we're just going to, not the fixture, the force. We're going to edit this definition. And we're going to reverse the direction. Now we're going the other way. 500 pounds of force and the other direction. We're just going to see if that made a difference. I'm going to go back to fixtures and add them all back. I'm just going to make one step to add these last 2 back in so we get all 3 again to make sure we get that like 6 value that I was looking for. And I'm pretty sure it didn't matter the orientation of it because it deforms the same way. Oh, oops, what did I do? It's probably the fixture. Let's make sure I got these right. Oh, see, that's all 3. See, I messed up. 1. Oh, I selected the middle. Let's just cancel that one. Delete you altogether. We're just going to go back and edit this one. So I have one face. Let's delete it just to make sure. 1, 2, 3. Check. So I have my one fixture, my new force. It's in the other direction. Next, 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 run. There we go. And that was pretty close to what we got. So it doesn't really matter the direction. We can run it either way just because of the symmetry of this part. All the fillets and everything are pretty much the same. So that's the spider. And you just need to answer those 3 questions onto the link. So now we're going to open up that one. Open up the link. No, don't save, because I just wanted the values. And I think on Dr. Foley's assignment, where are you? So that was the spider link. What is the maximum force that you can apply on each arm safely without the rib? With and without the rib. So there's the rib. This is what it's talking about, is this little piece right here. because that's actually bracing it. So the idea is this like is something that goes. I think it shows us where. Yes, it does. This is like an ink cartridge little piece right here. So the idea is that you pull these arms apart from each other to be able to get it to snap onto this little yellow thing right here. I don't know if I can make this any bigger. I can. You can see it's like some kind of a bracket type of thing that snaps into place here. So the idea is that you're bending this one that way and you're bending this one this way, and they want to know how much force you can put on this before it breaks, with and without this little rib, because this rib is reinforcing it so that it doesn't break as easy when you apply force to it. So that is what these instructions are talking about here. I can hit back. Oh my gosh, I made that so tiny. Oh, too big. There, right in the middle. So it wants us to assign this property stuff to it, and if you look, they're dirty and mean because they put it in centimeters squared, so we need to make sure we convert units here. I think ultimately we just multiply this times a million to get it to Newton meters is what we're going to want to do, if I remember right. Oh no, this one's times a million. This one's times 100 squared. So 100,000. Right? No, 10,000. All right, and then this one is just a ratio, so it doesn't matter. There's a unit list there. And then I think that was it on here. So they want to know the factor of safety. I think we need to remember to divide whatever we get at the end. It's by 2 and then by 2 again, because it's the maximum force. The way we're going to model it is we're going to put a force here and here, and then we need to figure it out. But ultimately it's per arm is the way this question is worded, so we'll have to divide it in half. But we'll go over all of that while we're going. So the first thing we need to do is do a material. So edit material. And I think I might just cheat because I have made these before, possibly. Oh, here's a plastic-like material. And it needs to be, yep, like I cheated. So all of this was from when I made it before. You see, so you multiply it times a million. And the yield strength. So yay, that made it easy. But ultimately, just make sure you use Google and convert these to the appropriate, because this is a Newton meter squared. These are Newton centimeters squared. They just want to make sure that you're paying attention, I think. So this was the correct values here on my screen. If you just want to take note of them, these are all in the Newton meter squared. But ultimately, it's just this one times 10,000, I think, and these two times a million. Or no, a million in the third one, and then 10,000 here as well. So apply and close. So now it's made out of that material, and now I'm going to launch my SimulationXpress. And I go into options. Does it tell me what units it wants it in? I don't think Dr. Foley specified either. But this is in newtons, so we're going to assume it's in newtons. That's what I'm going to do it in. Hit OK. And then hit next, and then hit add a fixture, and it's actually going to be fixated on this little thing here, because there's like a pin going through it, is how that picture should be interpreted, I believe. And then we hit next, and we're going to add a force. And we want to put a force here and here. And so here's where the instructions doesn't tell you how much force to put, because ultimately this part is kind of irrelevant, because I can literally fill out this with whatever value I want, and I just need to know that the results are whatever I filled out here per face. So I multiply it by 2, just to divide it by 2 later. I know it's silly, but so I put it on each face here, and I take this value, multiply it by 2, because that's the total force, and then I'm going to multiply it by whatever factor of safety it produces, which is going to give me the total force it can handle on both faces, and then divide that by 2 again, so that it's per face is the total force it can hold. So this part's actually irrelevant. It's just going to help me calculate it. So I'm actually just going to leave it as 1, because it's going to make my math easy. So 1 Newton on each face, and it's going in the correct directions right away. So I hit check mark. So actually it's technically 2 newtons, but to divide it by 2 right away, I'm just going to, in my mind, remember it's 1, so I don't have to do that extra divide by 2 step. And now the material is already assigned, and then I hit next, and I hit run simulation. And so I don't have to do the divide by 2. My calculation here is going to be per arm already. So I just take 1 times this factor of safety is how many newtons I can apply per arm of this before it breaks. I think I might actually go through and change this to pounds just because I'm American and I understand pounds of force better. And I'm going to make this 1 pound of force and hit check mark. And now I'm going to rerun the study. So we're going to do the same thing, and except I understand these results a little bit better because my mind works in pounds of force. So what can actually happen is each arm can withstand 11.9748 pounds of force applied to it. So the whole thing itself can withstand 1d to 23 something, if you just multiply this by 2, pounds of force with this rib in it. So I need to take note of that because that's the total weight one arm can have. So with a factor of safety, I have to divide that by 2, which is what Dr. Foley wants. So I take my 1 times this divided by 2 so that it applies my factor of safety per arm. And now I want to try it without the rib. So just similarly to what we did on that other assignment, we need to find the rib extrude, which is this Boss Extrude 1. And then we're going to right click on it. And I think there's a suppress feature. I forget where it is. Suppress right there. So if I hit that and I go back to my model, I can see it went away. And now I just need to rerun my study. I see it did it with the rib again. So I'm actually just going to start over. And I just got to fly through these parts again. Add my fixture. Put it back to English units because I want to understand the results a little bit better. I would even delete my material. You jerks. Good thing I have it saved. And now again, I can take my 1 times this divided by 2 for the second answer of this assignment. That was with and without the rib on each arm was the key there. And now on to the last part, which is the faucet. And I have that part as well. Open that one up. I don't want to save. It wants me to make it out of copper. Where's my material? There it is. Just copper, huh? Ooh, copper. And SimulationXpress. And I like pounds, so we're going to make sure we're in English. It doesn't really say, I don't think. Oh yeah, 100 pounds. So yay. So next. And then add a fixture. And this is where this would be attached and where the instructions tell us to do. And hit next. And we're going to add a force. An inward force of 100 pounds. So we want to add a force here-ish. So I want it parallel to that plane. So I'm going to put there. What I'm going to do is select from plane. Open up my design tree. Find the plane that makes sense. Zoom out here. I want my scroll bar works on that too. So from there. It's an inward force. We're going towards that plane, that direction of that plane. And it wants me to put 100 pounds of force. So check mark. So that was that. The material's already assigned, and I can run the simulation. So there it goes. And you can see very similar to what's going on in this picture. So Dr. Foley's assignment wants calculate the magnitudes of the front and sideways horizontal forces that would cause the faucet to yield. The magnitudes of the front sideways, horizontal. All right, so that was the front. So you take that times that is the value that you would have to apply to this for it to yield. So Dr. Foley's, so if you're reading the SolidWorks instructions, it wants you to apply a factor safety of 3. So then you can divide that by 3 and you can report that. But Dr. Foley's assignment actually says, because it pretty much follows the way SolidWorks is having you do it up until this last one. So it just wants to know the total magnitude. So you can either give me the total magnitude of the force that's applied here, or if you give me the divided by 3 number, I'll accept either one for the assignment since I'm grading them this semester in spring of 2024 only. So if you're watching this video and you're doing this, and depending on how you turned it in, just because the instructions were kind of contradictory between this document and the other one, I'm willing to accept either of those values, but you ultimately take this times this, and you can report that, or divide it by 3. And now the other one is we need to adjust the force, because he wants it from the side as well, so I hit edit definition, and instead of going towards that plane, what I'm going to do is I'm going to find a different plane. So hit delete, and it's this one, the right plane. So then hit check mark. And now we're going to rerun the study. And this is the exact same thing. You could either report this full number, or you can report it divided by 3 for the assignment. And that is finally the end of that. This was quite a long video. I hope you guys made it through it. You could probably watch it on twice the speed and get through it in 20 minutes. But that was the whole stress analysis lab. It was just being able to manipulate the different ways that we can approach this thing and making sure that we understand what we're rigidly fixating, where we're holding a part still at, and where it's not going to break, and then where we're applying forces. So when we model things, we have to smartly, because I can't say the word, smartly be able to tell SolidWorks how to simulate this stuff for us, so we don't have to do the calculations by hand. And the computer will always spit out a more accurate result, because as humans, we can make errors. But that was it for this video. Thanks for watching. I hope you made it through it, and I'll see you in class. Bye.